The Apollo moon missions are often remembered for high-visibility test flights and massive engineering triumphs. Yet the navigation computer that guided those flights was built by hand, using a technical process that mirrored traditional weaving. In the early 1960s, computers were massive mainframes that occupied entire rooms. They were constructed around glass vacuum tubes, which were not only bulky but also highly fragile and prone to breaking. When President Kennedy made landing on the moon a national priority, NASA engineers faced a physical crisis. They could not simply strap a room-sized, fragile computer to a violently shaking rocket and expect it to survive. The mission required a specialized form of memory that was compact, stable, and completely indestructible. It had to function perfectly while enduring the extreme vibrations of launch and the harsh environment of deep space. To solve this engineering impossibility, NASA moved away from modern machines. They turned instead to the meticulous precision of one of humanity's oldest manual crafts. The breakthrough was a technology known as magnetic core memory. This hardware relies on tiny ceramic cores. Magnetizing a core one way creates a 1, and the opposite, a 0. To manage data at scale, the coincident current system grouped these cores, threading wires in a 45-degree grid to create stable random access memory. Inventors like Anne Wang held the foundational core patents for this magnetic technology. But for the Apollo guidance computer, NASA needed a specialized version called core rope memory, allowing software to be physically hard-coded into the wire itself. This was the physical realization of software. If a wire was threaded directly through a core, the computer read a 1. If the wire bypassed the core, it read a 0. The density of this data was staggering, but it created a massive manufacturing bottleneck. In the 1960s, there was no machine capable of threading these fragile wires through thousands of holes the size of a pencil lead. The cutting-edge software capable of navigating to the moon was theoretical. It would only become functional if human hands could physically encode it with microscopic, error-free precision. To manufacture this memory, Raytheon recruited a workforce of women factory employees outside of Boston. The process was nicknamed the LOL, or Little Old Ladies method. Women sat on opposite sides of a panel, passing a wire-threaded needle back and forth to weave the binary code into the cores. The pressure of this labor was constant. A single missed hole meant a corrupted line of code that could crash the spacecraft, leading to a workflow that was inspected multiple times by federal agents. This need for extreme visual precision extended to the computer's integrated circuits. Manufacturing these early microchips required wiring complex geometric patterns onto tiny silicon chips. Fairchild Semiconductor sought out this specific technical skill by opening a factory in Shiprock, New Mexico, within the Navajo reservation. Most of the workers were Navajo women. They used microscopes and intense focus to place electrical components on tiny chips, creating intricate shapes that required painstaking attention to detail. Because this assembly work visually resembled traditional rug weaving, Fairchild Marketing Materials framed it as a feminine craft. Journalists followed suit, describing mission-critical electronics manufacture as a high-tech version of a traditional labor of love. This categorization separated the work from the high-status, high-paying world of engineering. By dismissing the labor as women's work, the industry justified lower compensation and withheld the professional recognition typically granted to scientific expertise. The ultimate test of this hand-woven hardware came as Apollo successfully landed humans on the moon and returned them safely to Earth. In 1975, a NASA report officially summarized the performance of the Apollo computing systems. The report declared the performance of the computer flawless, praising the versatility of its software. The indestructible nature of this woven memory was confirmed again following the 1986 Space Shuttle Challenger disaster. Months later, when the memory units were finally recovered from the ocean floor, they were found to be still functional. While core memory was eventually replaced by mass-produced semiconductors, it built the technical foundation for modern digital technology. The pursuit of a portable, stable computer for Apollo led directly to the devices we use today. Make no mistake, the transition from massive mainframes to portable, space-hardened computers depended entirely on this specific, skilled labor. This technical expertise turned theoretical code into functional hardware that could withstand the vacuum of space. For decades, the public image of the space race was defined by the men in white shirts sitting behind control desks. But the flawless performance of the Apollo computer is the legacy of thousands of women. Their untold stories challenge our understanding of what counts as scientific expertise and who exactly built the digital age.